I recommend you to download the tutorial handouts. There will be a lot of theory in this chapter. Okay, so for chapter 4, we focus on high temperature corrosion. In corrosion, since chapter 1, we mentioned some important element to initiate corrosion. Even in your test one, you was a question about to explain corrosion and what is the difference between electrolysis and corrosion process. So corrosion do not need additional electricity to trigger the process or to initiate the process. So you need three elements, at least a few elements. First, you need corrosion only happen at metals and alloy, or metals on pure metal and also an alloy that have a metal element. So you need metals, you need oxygen, you need hydrogen, you need water. So basically these four contribute to the corrosion, right? And in fact, as we go through other chapter later on, you're still seeing the effect of these four elements, metals, hydrogen, oxygen, water. And if you have these four plus another element, which is environment element, that will elevate the rate or make the corrosion rate faster. So in this case, we look at temperature factor. What happens if you have the four element and then you increase the temperature? So what will happen inside this high temperature setting? We fall under high temperature corrosion under chapter 4. Okay, so we'll talk about oxidation, sulfidation, carbonation, metal dusting, nitration, halogen corrosion, and few as deposit, molten and liquid metal. So from the wording itself, you know the first component, oxidation, it will focus on oxygen and some oxide, how oxide form. Second one, we talk about sulfur, sulfate. Third one, you see the carburization. Carburization it is linked with the carbonate structure, carbon structure, CO2, and so on. Metal dusting, we'll look at it later on. Metal dusting is linked to carburization. Okay, actually is the branch from this one. Nitration, from the name itself, you know that is linked with nitrate or NH3 or nitrogen. Halogen is linked with chlorine. Yeah, we focus on chlorine and so on. Few as salt means something. Salt means some a powder that trigger the corrosion. For example, NaCl, sodium chloride, and so on. Okay, molten, and then you know that we have a few state of solid. You can change molten because if you increase temperature, solid object or solid states, if you increase the temperature, solid will become liquid, right? So solid will become liquid. So on the process from solid to liquid, you get a molten state. And then what happens if you have a liquid states? What happened to the corrosion behavior? Okay, so this we will go through this one maybe this week or next week. All right, so it's quite a big chapter, but again, it's lots of theory. Try to when you study chapter 4, try to ask question. What do we have here? Means what is the element that we're talking about? What can this element do? Okay, so when you look at, for example, oxidation later, you always ask yourself, what is involved in oxidation? And then we talk about the element. What can all these elements do to the corrosion? And then where does this element come from? Okay, where does this element come from? Okay, and how do we control it? How do we control it in the industry? Okay, so we will talk about what is the element. We talk about where does this element come from that trigger the corrosion, and then we will look on a few chart, um, so that you get some idea through the researcher data. So I'll include some journals paper over here, and some if I can find in the context of Malaysia, then I will include the data in this chapter. Okay, let's start chapter 4. Section 1, we talk about thermodynamic principle first. Okay, first, just to recap, what is corrosion? Corrosion do not need electrolysis process. So what is so special if you compare to aqueous corrosion like we talked about previously, or yeah, the previous chapter, aqueous or environment corrosion. Well, when it comes to high temperature corrosion, the special things about this chapter is that um, for high temperature corrosion, it do not need liquid electrolyte, meaning there is no there's no medium, or there's no the metals element is not inside the solution, but is only because of the temperature. Okay. This chapter, or high temperature corrosion, we can also call them dry corrosion. Okay, we can also call high temperature corrosion as a dry corrosion or scaling. Okay, dry corrosion or scaling. So the word scaling, what is scaling is that when you open up the old heater and you look inside the copper tube, they will be like something white powder kind of things on the wall of the copper. So that is called scaling. All right. So most of the, if you want to find what is scaling, you go and find um, a water heater that use copper tube, or an old one, or damaged one. You go and open up the copper wire or copper tube. You look inside, you will see some white uh, white deposits on the wall of the cylinder. So wall of the tube. So that is called scaling. Next, we talk about the wording or definition of oxidation. Now, the oxidation itself, it focuses on oxide, formation of oxide, right? Or it talk about the process of forming oxide. All right. Okay, so these are all the textbook definition. All right. So for example, if you look at this diagram, so on the left is a normal metal. Let's say you have a block of metal like this, and then you have a layer of oxide that form under low temperature. Which is if you process a raw metals and then you put under a dry condition, it will still form oxide outside the metals, a thin layer of protective layer. You still have oxide. But what happens if you increase the same object with the oxide here? You increase the temperature, the oxide will go inside. All right, it will go inside the metals, and the process will increase at the contact surface of the metals, and then they will produce the chemical products along the surface. So that's why you see there's a increase of oxide on around the surface of the metals, and the core element is decreasing. The core element is decreasing. Okay, so this is how high temperature corrosion took place, and this laid the foundation of the following chapter, following session. All right, so always have this picture in mind when you have high temperature corrosion. Okay, and to start talking about high temperature corrosion, and we talk about oxidation, then you need an element called oxygen. Okay, when you have more oxygen in the around the corroding body, and this one is in a dry environment. That's why there's another name for uh, high temperature corrosion is dry corrosion. So the first element for today is oxygen. The first member of chemical is oxygen. So every time you see you see the wording of oxidation, oxidize, then oxygen come into the chemical process. Yeah. Okay, so we have done with some basic information or basic definition for high temperature corrosion. What is oxidation? What is the environment that allowed the oxidation to happen? Okay, next. Um, so where does this high temperature corrosion can take place? Or if you graduate later, you work in the industry, where can you find high temperature corrosion? Okay, so I'm going to give you all. So basically, you can see all the photo here is some illustration for the industry. So I give you all the answer here. Okay, so for example, power generation, the power plant that you have the change of sorry, you have a change of temperature in the process. All right, in the power plant, refinery, uh, engine, right? Engine, one of the most good example is in the aircraft engine or rocket engine. Okay, and also gas turbine, so something like that. So this is how gas turbine works. So you suck in air, and then there is a combustion process with the gasoline or with the fuel, right? So these are the section that will experience high temperature corrosion because of the uh, um, octane element and also the fuel element, chemistry element, and additive you add into the fuel. So the chemical process will happen over here. Heating and also mineral, okay, chemistry, refinery, automotive, pulp and paper, because you need to dry the the element when you process paper. Waste inclination means you process the waste. So these are the industry that you can find the evidence of high temperature corrosion. Okay. So in this chapter, you'll see a lot of example come from this list. You go into detail, the example that you can see and all this, right? So it will help you to get the idea. Next, we go into standard free energy formation versus temperature diagram. So we start to look at some research data. Okay, so we will have this chart. So again, this is a It is a small, it looks small on the screen here. So actually it's a very big chart, and even include this one in the tutorial handouts. All right. So the detail inside here is not that important, because you can download, or you can find out the detail of the lines of this chart. So what does this chart will give you? If you look carefully, there are some reading here, there's some reading here, there's some reading here, and there's some reading here. So basically, if you look at on the y-axis, so y-axis, it will give you some parameter. Let me see on my here, a bit smaller. Okay, on the left-hand side of the graph here, this chart is used for high temperature corrosion reference. Yeah? So on the y-axis here, y-axis here is for standard free energy reaction, delta G naught. Okay, delta G naught. And by the way, this chart is called Illingham diagram. Okay, so for high temperature corrosion, Illingham diagram is used to explain or to study high temperature corrosion, right? So remember this name, Illingham diagram is used to determine or to analyze high temperature corrosion. Okay, so y-axis over here is called standard free energy reaction, delta G naught. Is in the unit of temperature, or in the function of temperature, means it's related to temperature change. So inside here, you see all the lines here. What does all this line mean? It means you have all the process here. Huh? So just for your info, all these lines represent different chemical products can form under the conditions stated around the graph here. Okay, so it just tell you, all these lines tell you the line of stability of different chemical products. All right. But anyway, you can, if you want to know more about Illingham diagram, you can find in the lots of textbook, especially in the high temperature corrosion textbook. Right, very specifically focused on high temperature corrosion textbook. Then they will talk about Illingham diagram. But for this module, what is important is that you know what is Illingham diagram. You've seen it before. What is, you can picture or you can visualize what is Illingham diagram. Okay, it looks something like this. Okay, it looks something like this. And on the left hand side is the free energy reaction. And then around the body here is the environment. Is the environment that you have. Okay. So maybe I'll make it a little bit bigger. As you can see here, you have 4 axes there. On the left hand side, on the top, left, and bottom. So basically you have 3 lines here, 1, 2, 3, and these 3 lines actually surrounding the graph. Okay, surrounding the graph. So you have 3 measurement here. So okay, so the first line here, if you enlarge or you download my slide later on. So the first one is PO something, means it means for partial oxygen environment concentration. All right, means oxygen concentration. Means if you follow this line, you have 10 power something, 10 power something, 10 power something, and also you follow this line. Okay, and then you combine with the y-axis data, you will arrive at one intersection point for that particular metals products here. Okay, Again, all these lines represent the stability of the products. Okay, so in Ealingham diagram, what is important for this class is that you know what is happened on the y-hand side. What is y-hand side? Y-hand side is a delta G naught diagram. The unit is in kilojoule per mole of oxygen. So you learned about chemistry before. So kilojoule is energy. Per mole, you know 1 mole equal to a constant of number of molecule. And in this case, we focus on oxygen. So I highlight the area, right? Area. So the numbers is from below to the top. You see the arrow from below, from low number to high number. And again, this Willingham is to observe oxide. All these lines are referring to oxide. Yeah, it's referring to oxide. Example. The lower position of the lines on the diagram, it means the more stable the oxide it is. Meaning I take the two extreme example. You see this line and the last line here. If you compare the oxide on the top, there's a description on for the name here. So basically the concept is that if I compare this line and this line, so this oxide that fall inside this line is more stable compared to this one. And in fact, for the whole table, this oxide is the most stable compared to the rest of the oxide above it. Okay, so yeah, so this one you can look in more detail when you download the slides later on. Okay, so first graph for this morning, Ealingham diagram. On the left, it talks about energy level, okay, in delta G naught, okay, because the unit is in kilojoule per mole of oxygen. So it's energy level, you can say it's energy level. And then the rest is the environment you have. Okay. So I think this one is quite direct from the information on the screen here. All right. Okay. Now, you're familiar with this formula, right? Metals, M, metals plus oxygen, you get metal oxide. Again, this is just a very general equation, right? Metals plus oxygen, you get metal oxide. So we are assuming, because you know that when the metal and oxygen mix, there are lots of positive charge, negative charge process. But this is, we straight away use a very generalized equation where we just take metals plus oxygen, we get oxide. So you come up with this chemical equation, because you know that when those chemists learn about material science, they will go and measure the energy in the process, right? Through temperature, they will calculate how many joules or megajoule of that. So they use this formula. Okay, they use this formula. PO2 means oxygen, and you take the metals divided by metals oxide. It's a exponential component equal to E power your delta G divided by RT. Okay, and you can put in the logarithmic form, right? You know that when you have an E in your equation, you can flip the equation to written in the log format, right? You can remove the E by write this equation in the log format. So you can write log something equal to exponential something, right? So this is your mathematics log chapter. You write the E, you remove the E with the log. Okay, so what is important is that you understand that they are equation for the Illingham diagram. So this is the equation. Okay, this is the equation. So you see PO2 here. PO2 here is oxygen partial pressure. Oxygen partial pressure, where they can detect metals and oxide appeared in the experiment. Okay, that's why they take an exponential of metals compare with metal oxide. So it's a ratio of metals and the metal oxide. Okay. So this is another chemical reaction for Illingham diagram. Okay, again, Illingham diagram, what does it use if you want to describe it in the one sentence? Illingham tell you the stability of oxide, because all these lines, they are oxide. And on the left is energy. On the bottom, basically, they are connected line. They are the environment where you focus on. For example, the first line here is the partial oxygen partial pressure. Okay, and then let's say I just give you a free marks in the test or exam. I give you this diagram. I ask you, and then I label this line. I label this line. I label this line. I label this line. Maybe A, B, C, D. I ask you to arrange in sequence, stability sequence, from the most stable until the least stable oxide based on this diagram. You should able to answer. So this one, if I take this line compared to the last line, which one is more stable? Here, this one is the most stable on this graph. Why? How you link stability? You link with energy. Because all this line, all this line, you project to the left. Okay, you project to the left, you get energy, right? So when you have low energy for the formation of oxide, means it's stable. You need high energy to form the oxide, means it's a little bit, it's still stable, but if you compare two oxide, the top one will be less stable compared to the lower one. So if you go a little bit lower, means more stable. Okay, any question on the stability of oxide? Clear?
So far, no,
sir.
Okay, sir. Good. All right. So basically, this will be one of the way I ask question in test or exam. So I'm testing your understanding what is happening on the graph, right? I'm not interested to ask you about the chemical process, but at least you know how to apply this one. At least when you talk to corrosion expert, at least you have something in common. You know how to explain graph, right? That is more important to me. Okay, then we look at one table. One table that give you equation. There are lots of chemical equation that you can refer to, and their temperature range, and their energy change. In the energy change, the delta G, which is the y-axis that you can plot on the Illingham diagram. Okay, so let me show you the table 3.1 is a little bit of portion. It's just a portion, not all, but a little bit portion that will help you to generate Illingham diagram. Okay, let's see. Okay, so this one is add-on information. H2 over H2O. So you know that H2 is hydrogen over water. So where is this one? This one is the last line on the graph here. Maybe a little bit small, but you know that you have 3 lines to do comparison. Okay, 3 data to do comparison. So the first one is oxygen. The last one is water and hydrogen. The middle one is CO over CO something. Okay, carbon monoxide and the carbonate. Excuse me. Okay, now this one another line, CO over CO2. Okay, CO over CO2. Okay, so you have 3 lines. Oxygen, the partial oxygen, oxygen partial pressure, oxygen. The second one is the CO slash CO2. The third one is hydrogen and water. Okay, so these are the environment that you can read data if you have two data there. You have a change of energy and the environment here, then you do the intersection point, you arrive at that oxide. Okay, so how to use, for example, you're given some value that you can trace from the axis here. So let's say I give you some value, let's say this one. I give you the oxygen at this value. So what you do, you project or use your pencil to highlight this line. Then I give you some energy change. All right. So if the dot is here, let's say the dot is here, then if the dot is higher than the line, means there's a reaction happen here, because if fall below means you're already stable. Okay, if you high below the line means the products of the oxide is stable already. Okay, or you can predict what kind of oxide that you have, right? Depending on the material you have lah. Okay, this is the list. All right, at least you've seen this table before. You can find this table in the material encyclopedia and also in the corrosion handbook or standard. So you have all this long list here. Okay, so what basically when you have the thermodynamic data for reaction involving oxygen, this is for oxygen, meaning this data is to plot this axis, is to follow this axis, and then you plot the line over here with the energy. So you have the range of this one is temperature, the range of temperature, and you have the process forming the oxide, and this one is the energy in joule, the energy change in joule, and you give you the temperature here, okay, in Kelvin, in Kelvin. Okay, so basically there's one table that this is from the experiment. They measure from the experiment and then they plot into Illingham diagram. Okay. Okay, we have cleared the first chart, Illingham diagram. Again, when you talk about Illingham, you talk about oxide, formation of oxide, stability of oxide. The higher, the lower it go, more stable it is. Okay, if you compare the first line and the last line, so this oxide is more stable compared to the first line here. Okay, stability of oxide. On the left hand side, y-axis is energy, the change of energy, and the rest is just the environment that you done the experiment. Okay, there are three conditions: oxygen, carbon dioxide, and water or hydrogen. Next, we go into vapor species diagram. So when we talk about high temperature, when you learn about the changing of states, changes of material states, from solid to, if you talk about water or solution, right? So from solid then to molten, you reach a saturation stage, all right? Then you become gases and so on. So you have a lot of state. One of the state is become vapor. So during the high temperature corrosion, you have all these chemical reaction happen, all right? And all these species that appeared in a vapor form, they have a strong influence on the rate of attack. Okay, high temperature corrosion already happened, means corrosion already there already. But with the vapor species, they increase the corrosion rate. Okay, they will control the uh, they would dominate the high temperature corrosion rate. Yeah. Okay, so this is the researcher name. I just call them G and J. Okay, G and J. They have done experiment, and they focusing on the vapor species, especially for carbon, silicon, uh, molybdenum, and chromium. So I think I have some chemical diagram for you. All right. I think most of us, we are familiar with carbon. We are familiar with silicon, but not molybdenum and chromium. Okay. So these are the four members that fall into our content here because of this G and J research. Because we need something to talk about high temperature corrosion, and they have the data to support this kind of corrosion. Okay, so carbon, silicon, uh, MO, molybdenum, and chromium. So just get prepared. You will see these four members in the rest of the section later. Okay, carbon, silicon, MO, and Cr, chromium. So you see MO and Cr quite frequent in the later section. Okay, so I introduce you another four member. Okay, I think 15 minutes ago we introduced you one element, chemical element, which is oxygen, and then now we have another four. Okay, carbon, silicon, MO, and Cr, chromium. All right, these two are in common life. Is a chromium still there? Maybe MO is not very common for daily use, but they are there. They are there inside alloy material. If you use alloy metals, then you have this element there. Okay. You have 6 types of oxidation phenomena. So I list all here. Again, it's a lot of information today. So let's go one by one, right? So basically, the 6 types of oxidation phenomena, you can derive them, or you can separate them into 3 zones. One is low temperature. Second, moderate temperature. The next one, it will be high temperature. So 6 types of, though there are 6 types of oxidation phenomena, but you can explain them using 3 zone, 3 temperature zone: low temperature, moderate, and high. Okay, low temperature, moderate you have 3, high temperature you have 2. So during low temperature, low temperature, what happened to the high temperature the corrosion process? At low temperature, you focus on oxide film. So you know that when corrosion happens, there's a protective film form. So when at the oxidation phenomena at low temperature, you focus on oxygen and metal species, the reaction between the contact between oxygen and metal species. Okay, which is the when you talk about low temperature means you talk about the initial process of formation of oxide. And how oxide form is oxygen plus metal species, like the formula that we seen just now, M plus O2, you get MO2. That is under um, low temperature phenomena. Okay, then we go to high temperature first. Then because moderate one is in the medium, right? So we go for low temperature and what happened at high temperature. So when you have high temperature, there are two phenomena you can observe. One is the oxides, something happened to the oxide and your metal oxide will be destroyed in a very high temperature. You just imagine the changing of state of that chemical element, right? You imagine as an ice cube, as a water formation. So at low temperature, you get ice, right? At low temperature, you get ice. So solid is a solid formation or solid states. So how you get ice cube? You form two things together, oxygen and the metals. Then you get solid states. At high temperature, something happened to the oxide. So you imagine ice cube when it increased to very high temperature in the boiling temperature. What happened to the cube? It will melt into liquid form, right, or molten form. So these two phenomena is happen in the liquid form or in the molten form. And then in the middle of low temperature and high temperature, there are three process here. Okay, so it just gradually increase what happened to the oxide film. Okay, for the moderate to high temperature region, you focus on what happened to the oxide film. Okay, so the first phenomena you see when you start to enter into moderate temperature, something happened to the oxide film, and oxide they will start to form, and then after that, as you increase more temperature, you know that oxide is something that brittle, something that it become hard, right? Oxide is something very hard, like a carbon. You imagine as a carbon powder, so or carbon film. So they are more easy to crack, become cracked, because if they increase the temperature, they have more energy. Then this oxide film and the oxide will form crack when they keep increasing the temperature. And then after that, when you produce more energy, you know that after you have enough energy, you will see gas form, right? You will see gas form. So the oxide will change to oxide gases. Will change to oxide gases. Then when you go into high temperature region, you will see all the oxides will be gone, and there is a removal of oxide over here. Okay, textbook they use volatilization. Volatilized oxide means very high energy oxide. Okay, and they can go away from the surface of the metals. Okay, so these are the oxidation phenomena that you can try to visualize. Sadly, I don't have the diagram for this 6 type, but you can imagine based on temperature region here. Okay. This is another chart for you. When we talk about vapor species, they are plotted in log format. Okay, again, you still remember there's one equation just now that we transform into log form. I'm not sure you still remember. Let me recall the equation. This equation. Okay, so from Ellingham diagram, when talk about oxide, they use this equation to do calculation. So you change something equal to E power something, you can change this equation with the E to log form. So you remove the E by rearrange the equation and calculate in the log form. So this is on the left hand side and right hand side. You know that when you have an equation, you can plot graph, right? So how you plot graph, you have y and x axis. So when you plot graph, for example, y equal to ms plus c. So this is y equal to mx plus c. So this is y equal to x. Okay, y equal to x. So, or you can flip. Okay, you can flip either this one become x, this one become y, but basically you have a linear equation over here. Okay, so as you can see here, if you look at this equation, you look in the perspective of mathematics. If this one is your y, or let's say this is your x equal to y something, or y equal to mx. So basically you can plot your y in this one equal, let's say your x is delta G naught. So your gradient will be 1 over RT, right? If your delta G is your x value, so your y equal to mx, your gradient will be 1 over RT, your x will be delta G naught. So basically you can plot y equal to something x. But you can flip the relationship by plotting the axis here, because if you look at this graph here, Ellingham here, your y-axis is G. Your x-axis here is your log something. So basically you use this information to plot graph like this. Okay, so I hope you can, from this mathematics model here, you can see the relationship, how you transfer this one into graph form. Yeah, basically you see this as a simple mathematics. You're plotting a linear equation here. For example, y equal to mx plus c. So this one don't have c, have c lah, but c is all the intersection point, but we are not interested on the c at this moment. So you can see that we have your x, this one is your x, this one is your y, but you can flip. You can flip. So to plot the y and x axis. All right. Let's go back to the chart just now. Okay, so that's why the chart just now, they can plot log something and log something. So in this graph is log P on atmospheric pressure, ATM 1 atmospheric unit. So here is minus 0. So you can see this one is minus atmospheric. So it's you can say as a vacuum, not vacuum, but it's a negative pressure kind of environment. It's a negative value. And then this one is the PO2, means you're talking about oxidation. There's oxygen there. So it will tell you at certain level. For example, on this graph is you see Cr, chromium. Just now, the 4 member just now, chromium stable, and this one stable, and so on. So you can read from this graph here. So this one is for chromium oxide system that they done on research. So you can plot all this line on the graph. And this one is very high temperature, 1250 Celsius. It's quite high. Okay, I think we stop at vapor species diagram. Then we go for a short break. After that, we go into two-dimensional isothermal stability diagram. Okay. Okay, let me stop the recording.